Hey students, in today's lesson, lesson 8.6, we're going to be looking at radical expressions and rational exponents. So we think of radical, we think of like that root sign, and we think of rational exponents, we sometimes call them fractional exponents. Those are the exponents that have both a power and a root all in one exponent. So our learning goals are to rewrite radical expressions by using rational exponents. That's actually something we've done before. And then simplify and evaluate radical expressions and expressions containing rational exponents. That's a lot of R's. Radicals, rationals. So we're going to simplify and evaluate radical expressions and expressions that contain rational exponents. So the nth root of a real number can be written as the expression here, the nth root of a, where n actually indicates the index. So if there's not an index, that's implied that it's 2. And if it's 3, then that means it's cube root. If it's 4, then it's 4th root. If it's 5, then they're taking the 5th root. And again, if the index is left blank, that means that the index is 2, and that's the typical square root. And that number that's underneath this a here is actually called the radicand. Let's just get a little terminology here. So this box basically here just tells us the numbers and types of real roots that we might have. So when we think about, like, when we're square rooting things, we know that we always, except for in one case where we're square rooting 0, we always have a for square rooting a positive number, there's always a positive and a negative square root. So if we kind of took that a little further, in general, if we have an odd index, like say 3, 5, 7, something like that, odd numbers, then we will get exactly one real root. So an example of that would be the real third root of 8 is 2. So we take the third root of 8, the only number that multiplies by itself 3 times to get 8 is 2. If we have an even index instead, and we have a positive radicand. So if we're trying to take an even root, like square root, 4th root, 6th root, or whatever, and we have to have a positive radicand, that means the number under the radical has to be positive, because otherwise we're going to be getting imaginary roots, right? And we're just talking about real roots. So then we'll get 2 real roots. One will be positive and one will be negative. Here's an example. The real 4th root of 16 are 2 and negative 2. Or the real square roots of 16 are 4 and negative 4. Now if we have an even index, okay, so 2, 4, whatever, then that, and we have instead a negative radicand, we will have 0 real roots, because remember, they're imaginary roots. So if we ask for real roots and you have a negative radicand under an even index, an even radical, then that means that you're not going to have any real roots. But if if you are taking you have an odd index, like you're taking a cube root or 5th root or a 7th root, you can have a negative radicand. Like you can take the cube root of negative 8. It will just be negative 2. Because you could have an even number or an odd number of things multiply and give you a negative number. That's the problem with an even index. You can't multiply an even number of negative things and get a negative. Okay? Or an even number of positive things and get a negative. And if the radicand is 0, that means if the number that's under your radical with any kind of index on it, you're always going to get 0. So the square root of 0 is 0, the cube root of 0 is 0, the 10th root of 0 is 0, whatever. So if your radicand is 0, your root is always going to be 0. That's important to note because in some cases, you might be getting 2 solutions, and some you're getting 1, and you have to be aware of when that's going to be the case. So if I ask you to find the 6th root of 64, and it says to find all real roots, so I've got an even index, my radicand is 64, so I'm thinking of a number that multiplies by itself 6 times to get 64, and I know that's plus and minus 2. Okay. Now, if you're not quite sure on some of these, you can go to your calculator and you just have to go under the math menu and you'll have to use, so like you'd have to type it like this. You'd type the 6 for the root, then you'd go under the math menu and you'd use, so you go under math and then you'd go down to the button that looks like, or the choice that looks like this. It's got, I think it looks maybe like that. It's got a little X out in front and a root sign, and then you can type in your 64. Okay, now it's only going to tell you that it's positive 2, but you also have to know that it's negative 2 as well. So your two roots. One comes from the calculator, if you're going to use the calculator, and the other one comes from just kind of common sense to know that a negative 2 multiplied by itself 6 times will also give us positive 64. Okay, so what about the cube root? So that looks like this, the cube root of negative 216. So there's actually a cube root key under the math menu. So if you go under math, key, and then you'll find a cube root key. It looks, just has a 3 out in front like that, and then you can just type in your negative 216. If that's not one that's really familiar. And anyway, it will tell you that it's negative 6, and that's the only solution that there is. So when it's an odd root like that, the calculator will give you your answer directly. There's no other possibility, because a negative 6, if you multiply it by itself 3 times, will still give you a negative number, and it gives you negative 216. And how about the fourth root of, so we start off with the index of 4, fourth root of negative 1024. Well, remember that it said we want the all real roots. Well, there are no real roots, so we'll have to say no real fourth roots, because we have an even index, but we have a negative radicand. And so that kind of relates to right up here where we would have no real roots. Okay, let's turn the page. Think back when we studied these rational exponents. And so if I had an expression like this, the fifth root of negative 32 to the third power, if I wanted to write it in radical form, okay, so first I write it in radical form, it would look like this. That is the radical form. Now, rational exponent form, if I wanted to do that, that's asking me to do this down here, a rational exponent, fractional exponent, it would look like this, the base, which is negative 32, and that negative 32 is being raised to the, okay, the power goes on the top, so the higher power on the top, so that would be a 3, and then the roots grow under the ground, so the roots on the bottom, so this would be negative 32 to the 3/5. So that's how we'd write it in rational exponent form, but in radical form, it's this, fifth root of negative 32 to the third power. There's really two approaches to evaluating this. If we want to evaluate it by taking the root first, so I would take the fifth root of negative 32, and then whatever I get, I would raise it to the third power. So that's how I'm thinking about it. Well, the fifth root of negative 32 is negative 2. So this really means negative 2 to the third power, and negative 2 raised to the third power would be negative 8. So my final answer is negative 8. Now if I try to do the other method, okay, that means I'm going to evaluate the power first. That means I'd have to raise negative 32 to the third power, and then take the fifth root. So I'm not going to do it that way because that just is really cumbersome. It makes a really big, a large relative value, because negative 32 to the fifth or to the third power is going to be pretty significant. So it's much easier to evaluate the root first. So I'm always going to advocate for method 1. Evaluate the root first, and then whatever you get raised to the power. So let's do a little practice with writing expressions in radical form. So this is written in rational exponent form, 64 to the 1/3 power. And so if I wanted to write, I know that the radicand is going to be 64. I know that the power is on the top, so that's raised to the first power, and the root is on the bottom. So this is the cube root of 64 to the first power. And so really, since it's to the first power, I don't even need to list it. I can just write that as the cube root of 64. This next one, the radicand would be 4. And so then now the power, which is on the top, is the 5, and the root is 2. So this is actually a square root, and if it helps and you want to put the 2 out in front, you can certainly do that. But it's the square root of 4 raised to the 5th power. That's one way to write it. Now you could also write it like this. You could write it as the square root of 4 to the 5th power, put the power underneath. That's fine too. So I want you to pause the video and you try C, write it in radical form. Remember, the powers are up high and the roots grow below. Okay, so this one could be written either one of these ways. Probably the most likely is the one I wrote first. And again, even especially to evaluate it, you definitely wouldn't want to raise 625 to the third power and then have to take the fourth root. Now in this next example, we're going to go the opposite direction. So this time we're going to write expressions using rational exponents, but they're written in radical form to begin with. So when we write in exponential form or rational exponent form, we have to figure out what is the base. Well, the base is the radicand when it's written in radical form. So my base is 13. Now remember that the way they're set up is power on the top and roots on the bottom in terms of our rational exponents. So the power of this is the 4 and the root is 8. Well, it turns out that the exponent 4/8 can be reduced. It can be reduced to 1/2. So raising 13 to the 4/8 is the same as just raising 13 to the half. Let's make B a you try question. So pause the video and rewrite this one using rational exponents. Pause the video now. Well, we could rewrite that as 3 to the 15/5, which is the same as saying 3 to the third. And just on a side note, if we wanted to find the value of that, that would be 27. Let's turn the page. So in this next example, we're going to apply some of the power properties that we know that we reviewed at the beginning of this trimester. And so in example A, we're multiplying two powers and they have the same base. So when you multiply and the bases are the same, we can combine them together as just one single base by adding the exponents. So we're actually going to add 7/9 and 11/9. Well, if we add fractions, we need a common denominator, which they have, and then we add the numerators. So if we add the numerators 7 and 11, we get 18, and that's 18/9. Well, that's the same as just saying 7 squared, or 49. When we divide two bases that are the same, we have to subtract the exponents. So we're going to be subtracting, because we have the same base, so our base will still be 16, but our exponent will be the difference between 3/4 and 5/4. Well, they have the same denominator, so I can subtract them, and when I subtract, they give me an exponent of negative 2/4. Or 16 to the negative 1/2. And remember, that's the same as saying 1 over 16 squared. I'm sorry, 1 over 16 to the 1/2, my fault. And since 16 to the 1/2 is the same as saying the square root of 16, and that's 4, then I really get 1/4. Actually, and technically it could also be negative 1/4. So those are my two possibilities. Now with C, we're raising a power to a power. When we raise a power to a power, we actually have to multiply. So we're going to be multiplying those exponents, and the base will be 64. So if we multiply the exponent of a half by the third, I actually get 1/6. So we know that that's really the same as taking the 6th root. That just means taking the 6th root of 64 and raising it to the first. So the 6th root of 64 is 2, or, as we saw at the beginning of this lesson, it could also be negative 2, because we're taking an even root of a positive number. So my two solutions are 2 and negative 2. So here are some for you to try. So try the 3 you try questions, D, E, and F. And when you're done, tune back in and check your work. All right, so thanks for trying those. Check out the answers. 25, 6 or negative 6, and finally F is 2/3. Example 5 asks us to simplify some radical expressions. So you may remember that when you have a radical and you can split the radicand up into factors, then you can separate them off and give them their own radical. And what I mean by that is, if you have an a, I have under the radical, I have 81 and x to the 12th. Well, what I could do is I could separate, that's a product, I could separate these off from each other and give them their own radical sign. So if I wanted to simplify the 4th root of 81 to the 12th, I could just look at these separate pieces for my answer. So I know that the 4th root of 81, if I think about that, that's the number multiplied by itself 4 times, I get 81, that's 3. If I look at that next part, the 4th root of x to the 12th, I know that this is the same as saying x to the 12 fourths. And x to the 12 fourths is just the same as x to the 3rd. Now technically, this 3 could have been plus or minus 3 because I'm taking a 4th root of a positive number. So just to be safe, we might want to put a plus and a minus out in front and just to indicate it could be a positive, it could be a negative. Now we're going to go ahead and skip example B because it really is the same type of problem. Now let's look at example C. So we'll just write a little skip next to this one. We're going to skip this. Example C, we have 2 cube roots that we're multiplying. Well, probably our best bet from the start, if we looked at these and they're not really easy to simplify separately, is to multiply them together and then look at the product. So if I multiply these 2 together, I can write that as the cube root of, well, x to the 7th times x to the 2nd is x to the 9th power. So what this is really saying is x to the 9 thirds, or x cubed. So I can multiply radicals as long as they're like radicals, and as long as they have the same index there. Okay, taking a look at example B, there's really 2 approaches. It all sort of depends on what the expectation is in terms of the final answer. When I think about this, the 5th root of x to the 7th, I know that that's the same as saying x to the 7/5. But what if you were not allowed to write fractional exponents? Let's say we wanted to only have integer exponents. If that were the case, we kind of think about this like simplifying radicals that maybe are not perfect squares or perfect cubed or whatever. So if we kind of thought about taking the 5th root of this x to the 7th, but if we thought about it instead of x to the 7th, we thought about it as x to the 5th times x squared, which is really the same thing. I'm just splitting it up so that one of these exponents is a perfect 5th root because it's, if you raise x to the 5/5, it just turns out to be x to the 1st. So then I could kind of split them off and give them their own radical and then deal with the one that I can actually simplify. So I could take this part, which is the 5th root of x to the 5th, and that just cancels out, it's x to the 5/5, which is x to the 1st, or x, and then I could just leave the part that I couldn't simplify under the radical. So that's what my final answer would look like, x times the 5th root of x to the 2nd power. So with that same thing in mind, when we used to simplify square roots, if they weren't perfect squares, well, what about if we wanted to simplify a cube root? We know that, well, you may not know, but 250 is not a perfect cube. But if we wanted to simplify this, we could think about if there's a perfect cube that is a factor of 250. And I know just a few perfect cubes I kind of keep stored in my brain, and one of them is 125. So I know that 125 goes into 250 2 times. So I could rewrite this as the cube root of 125 times 2. Well, then I could split them off and give them each their own cube root, own radical, and now I could go ahead and take care of the part that is the perfect cube. I know that the cube root of 125 is 5, so I could just write this as 5 times the cube root of 2, and that would be considered simplified. And then this final example, F. Well, you may remember back when we were looking at say, for instance, with trig ratios, when we had some of the exact values and we had a radical on the denominator. And we said, well, that's not okay to have a radical in the denominator. And so we would multiply the top and the bottom of the fraction by whatever that radical was to kind of cancel it out of the denominator. Well, So in this case, same thing. I've got 3 over the 4th root of x. Well, it's not okay to have that radical on the bottom. But in order to cancel out a 4th root of x, like when we want to cancel out a square root, say we had something like this, 1 over the square root of 2, let's say, we would have to multiply by a square root of 2, and that's because then that gives us 2 of these to pair up, and that ends up making the bottom really the square root of 2 squared. And so we needed a partner to go with it so that we had 2 of them, so it was squared. Well, if you think about that, if we look at this radical, we have a 4th root of x. Okay, if we only multiply by a 4th root of x, another 4th root of x on the bottom, then we have the 4th root of x squared. Well, that squared isn't going to cancel out the 4th root, so we actually have to do this 4 times. And we'd have to do another one, 4th root of x, and then another one, a 4th root of x. And so we'd have to do that same thing on the top. So essentially what we're doing is we're just making sure that we have 4 total 4th roots of x on the bottom so that they cancel out. Well, that would be the same as just doing this. Multiplying by the 4th root of x cubed. And then you could do the exact same thing on the top. You could multiply by the 4th root of x cubed. So essentially you're just multiplying by 1. So now what that does is it makes it so that I have 4 of these down here, and so that when I combine them, it's the same as saying the 4th root of x to the 4th. And now it's going to cancel out that 4 out in front. So that's what I want to do, is I want to multiply by however many more 4th roots of x that it would take to cancel out. So that leaves me on the top with 3 times the 4th root of x cubed. And that bottom now just becomes x. So we have 3 times the 4th root of x cubed on the top, and we just have x on the bottom, and that's our final answer. So let's go ahead and turn the page, and we'll just talk a little bit about what's remaining in the guided notes here. The next 2 pages in your guided notes really are just more problems to practice utilizing these properties. And so what we're going to do is we're going to designate these as our in-class examples. So if you want to just go ahead and label them in class, and this is what we'll pick up on when we meet in class. So I'll see you then.